We've so far seen how to calculate volumes where we're given either an explicit formula for the cross-section, or if I know my solid is some solid of revolution, and I can find a nice formula for the cross-section that's perpendicular to the axis of rotation. The question now is that always the case? Or are we going to need some new tool? Let's examine the curve y equals 2x squared minus x cubed. And let's say I want to find the volume of the solid that is obtained by rotating the region under that curve around the y-axis. Since we're rotating around the y-axis, normally we'd look for a cross-section that's perpendicular to the y-axis. But here, it's not at all obvious what's going to be my inner and outer radius. Our first problem is the same function determines the inner and outer radius, and writing this curve in terms of y, so finding the inverse function of 2x squared minus x cubed, is not going to be easy for us to do. However, we can very easily find a slice in which y equals 2x squared minus x cubed is my top curve, and the x-axis is my bottom curve. So finding the length of the red line oriented parallel to my axis of rotation is very easy to do. But my problem is that's not perpendicular to the axis of rotation, so our washer method's not going to work. But let's see what happens when we rotate this anyway. So this red line, in which my curve y equals 2x squared minus x cubed is going to play the role of my top, the value for the top of my red line, and the x-axis is going to play the role of the bottom. So my slice is the distance between the curve and the x-axis. When I rotate this, I'm going to get some cylinder. Okay, so I'll get some sort of cylinder that's hollowed out. So I'll get a carved out cylinder. And let's explore this carved out cylinder. So this cylinder, if I cut it open, okay, I can find that it's going to have the same volume as some rectangular prism, where the length of that rectangular prism is going to be the circumference. The height of that rectangular prism is going to be determined by the distance from the curve to the x-axis, so the height is going to be played by y equals f of x. And then the thickness of that rectangular prism is going to be my delta x. Okay, so that's just going to be what I'm going to choose. All right, so how many shells I'm using to approximate this volume is going to determine my delta x, and that'll be the thickness. So then the volume is the circumference times the height times the thickness, or 2 pi r, so the radius, times the height times delta x. And in this case, the radius is just the distance from that red line to the axis of rotation. That's the y-axis. Well, the distance from the y-axis to some point x is just going to be x. So the volume of my shell is 2 pi times x times the height, which is 2x squared minus x cubed, times the thickness, which is delta x. So we know the volume of one shell is going to equal 2 pi r times height times delta x, which means my total volume I can approximate by taking more of these shells and adding them together. It's in a Riemann sum. So I'm going to get, if I have n shells that are going to approximate my volume, then I'm going to get the sum from I equals 1 to n, 2 pi r times h times delta x. Then to recover the actual volume instead of the approximate volume, I'm going to take the limit as n approaches infinity of my Riemann sum, and I'll recover that the volume will be the integral from a to b of 2 pi times some radius with respect to x times some height with respect to x dx. So what does this look like in practice? In the simplest case, our volume is going to be obtained by rotating about the y-axis some region under the curve y equals f of x from a to b. In that case, my volume is going to be the integral from a to b. My circumference now is just going to be 2 pi x, because the radius will be equal to x. My height will be determined by the value of the function, so I get the integral from a to b of 2 pi x times f of x dx. So in our picture here, if I take some slice, like my red line here, the distance to the x-axis, the distance from the y-axis to that red line is going to radius equal to x. The height then is determined by the value of the function of x, or f of x. So my height is 2x squared minus x cubed. So again, the circumference is just going to be 2 pi x, and the height is going to be f of x. So I'll get the integral from 0 to 2 of 2 pi x times 2x squared minus x cubed. So to recap, what we want to look out for is our shells are going to be oriented so the height is parallel to the axis of rotation. If we rotate around the y-axis or some other line like x equals a constant, then we will integrate with respect to x. This is very different from the washer method. I also want to point out that the circumference is not always 2 pi x. As in the washer method, our radius is going to be determined by our distance from the axis of rotation. And our height is not always given by a single function. Similar to the washer method, if we are looking at a region enclosed by two functions, then our height will be determined by the difference between those two functions. So again, this is similar to what we had to do to find the inner and outer radius for the washer method. So in summary, what we're going to do is look for obvious equations for either the distance between the top and bottom functions or the distance between right and left functions, and that's going to determine whether we're going to want to use the washer method or the shells method. And there'll be 2 more videos to get into these issues in depth.